this week we're going to be talking about the CHSH scenario, except we're going to do so in a way that sort of captures some of the ingredients that we will need going forward into talking about contextuality. So in particular, we sort of want to go through the CHSH scenario, the parties, and then go forward and talk about this notion of global outcome assignments, which becomes important when we talk about contextuality more broadly. But I want to sort of frame it first in terms of CHSH, which is maybe a little bit more familiar. So the idea is that we are going to have these two distant parties that we've talked about, Alice and Bob. They each have two inputs and two outputs. So for each, I will say the inputs are 0 and 1. And for each, I will say the outputs are also 0 and 1. Then there's also the notion that I will call Alice party 0 and Bob party 1. And the idea is that Alice and Bob, as we know, are very far apart. But what's going to be kind of interesting when we go towards contextuality and discussing that within that framework, what is really important here is that the observables, if we think of it in the quantum case, are going to be commuting with each other, and that the marginal distributions agree on their overlap. So actually, many of the features that we have here are just special cases of what we consider when we go to contextuality scenarios. So I'm going to want to sort of introduce a little bit of notation first, just so we can get started. In particular, I want to consider something, a measurement context. This is just going to be what I've previously been calling a measurement setting, and it's just going to be a pair of x0, x1 in 0, 1. Ultimately, Alice chooses one of her measurement inputs, Bob chooses one of his measurement inputs, and we just call that tuple x, or x0, x1, each of which can be in 0 or 1. And then we also have, for each particular x, we have the outcomes. Now, this is what you would observe in an actual empirical scenario. You just have the zeros or ones, so I will call this Sx equals Sx0, Sx1. Okay. This is the outcome when the measurement input or context x is chosen, and you get outcome Sx0 for Alice and Sx1 for Bob. Now, this is a little bit of overload on the notation, so often I will just write Sx equals S equals S0, S1 to distinguish between Alice and Bob. So what we have here is an empirical scenario. We have some measurement inputs, we have some measurement outputs, and what we have then is a collection of probability distributions that are going to be called So what we have here is a collection P of S of X for all S and all X. What do I mean by this? And we're going to call this thing a non-signaling distribution. So where are these coming from? These are precisely every time I choose an X, a pair like this, I get some outcomes, which are some S. So there's going to be 4 possible inputs, each which have 4 possible each which have 4 possible outcomes. So this is called a non-signaling distribution if, so there's 3 conditions. We have that P of S of X greater than or equal to 0 for every S and X. So I'm just saying that all my empirical probabilities have to be non-negative. You can think of this maybe more heuristically by saying, how did I collect these empirical probabilities? Well, I ran this experiment a bunch of times and I tabulated some frequencies. Of course, these should be non-negative. 2, we have P of S of X equals 1 for every X. So this is sum over S, just saying that these probabilities should be normalized. And 3, we have non-signaling. So this is non-negativity, normalization. And then we have, for example, that P of S0 of X0 is equal to sum over S1 of P of S0, S1, X0, X1. So if I sum over all of these outcomes of Bob when I'm looking at Alice, then this should not care about whether I sum over with X1 or with some other input, X1 prime. So in fact, to just be very specific, this could just be 0 because there's 2 options, S1 P of S0, S1, X0, 1. And similarly, so these are called the non-signaling conditions, similarly for Bob. So there's 3 sort of conditions that we sort of require on the probabilities that we get here, and we call when these are satisfied, we call these non-signaling distributions. Now, it turns out to be the case that we're going to be able to distinguish between 2 types, things that are called more or less classical, and also ones that are going to be, so classical or local versus non-classical, i.e. non-local in this case. So we have that the set of probabilities, so there's n is going to be the number of empirical probabilities. This is the number of probabilities in this set. Sorry, this is just this, which is equal to, well, there's the number of measurement settings is 2 squared times 2 squared outcomes equals 16. So this is the number of total empirical probabilities. So I can think of a non-signaling distribution P. In an abusive notation, I will also say that this thing is also an element of Rn, where I take each coordinate vector, E corresponds to some P of S of X, so unit vector. And so in particular, we can define this thing, NS. So right now I'll put this in quotes. The set of all non-signaling distributions. And since each non-signaling distribution can be thought of as a vector of length 16, basically what do? I take these probabilities and I just pick some ordering for them. So maybe I start with the 0, 0 setting and go 0, 0, 0, 1, 0, 1, 0, 1, 1, and just do this 4 different times. So I can think of NS as being a subset of Rn. So in fact, we have this. NS is a convex polytope. So I'm just going to sort of quickly go through why this is. It will be useful to think of, to have a sort of idea of what the geometry of this thing is a little bit. So let's go through the proof just quickly. And the major idea here is there's a couple of things that I really want to emphasize. One, just to connect with previous things that we've talked about, what would it require for this thing to be a convex polytope? So first, we need this thing to be obviously convex. We need this thing to be a polytope. What does that mean? It means it has to be a bounded polyhedron. So in 3, it should be polyhedron. Okay, so 2 of these we're going to be able to hit at once, which is the following. So for 1 and 3, the fact that when we look at the ingredients that go into a non-signaling polytope, what do we need? We need that these are non-negative. So what do I have? I have a finite set of inequalities, half-space inequalities. These things split my space into 2, those for which the probabilities are non-negative and those for which they are non-positive. So we have that NS is greater than 0 to n. This is the positive, what's called maybe orthont. Basically, this is like the positive part of a quadrant, but in higher dimensions. So how does that help us with 1 and 3? Previously, in one of the lectures, we talked about how a half space is itself a convex thing, because if I have one point and another point which satisfies some inequalities, then they're convex mixtures too. So, so for 1, we have intersection. So maybe I should say half spaces are convex. And 2, the intersection of half spaces, the intersection of convex is convex. So and 3, so maybe I should use a different numbering for this. 1, 2, and also a convex polyhedron is the intersection of half spaces. So we have here that the non-signaling distributions are defined by these half spaces. Half spaces are convex. The intersection of convex stuff is again convex. So we have this. And then a convex polyhedron is just the intersection of half spaces. So we get 1 and 3. To show that it's also bounded, for this, what we need to do is notice that our probabilities are also normalized. So number 2 implies that P of S of X, we know that each of these is non-negative, and because the probabilities are normalized, they can only be at most 1. So that means that we're looking at coordinates that are within this cube in Rn. Now, that's not going to tell us the full picture of the geometry of the non-signaling polytope because there's also these non-signaling constraints here. And these things actually are what make it have some very interesting sort of character. But at this point, the fact that we have a polyhedron that's bounded is enough to tell us that it's a convex polytope. So we've actually already proved this. So I will get to the non-signaling constraints momentarily, but for now, we have actually proved this already. Okay, so one thing that I want to get to now is, so we have this thing, it's a convex polytope. What is the dimension of this thing? Because this will be relevant for us later on. So we have some point P, which is in Rn, but then this is not enough because we have some constraints. We have 4 normalization constraints. What is the effect of these things? Well, let's just take one for example. So you have P of 0, 0 given x plus P of 0, 1 given x plus P of 1, 0 given x plus P of 1, 1 given x equals to 1. So I can also think of this as just reducing the number of coordinates I have to deal with effectively by solving for 1. So just say P of 1, 1 given x is equal to 1 minus the remainder, P of 0, 0 given x minus P of 0, 1 given x, and it's P of 1, 0 given x. So these constraints, what do? They reduce the number of effective parameters that I need, and thereby reduce the actual dimension of the polytope that I'm considering. Okay, but that's not enough because I still have some more constraints, and now I also have 8 non-signaling. We will see, it'll be easier to see in a moment that there's 8 of these. Maybe in fact, yeah, in fact, maybe it will be useful to introduce this box notation. Box representation, perhaps. So, for a given x, so fix some x, what you can do is create a table in which these probabilities are. So for a given x, we want to write P of x of 0, 0. This is when S0 equals 0, S0 equals 1, S1 equals 0, S1 equals 1. So Px 0, 1, Px 1, 0, Px 1, 1. This is for a given x, I can write a singular box. Now I can think of actually representing all 16 of these probabilities. So when I think of this as being in Rn, I have a vector of 16 numbers. I'm just arranging those in a particular way. So a full non-signaling distribution can be written in this way. So each of these boxes are going to represent a different x. This is x0 equals 0, x0 equals 1, x1 equals 0, x1 equals 1. And now in each of these boxes, I put one of these. So now I have a P00, S0, S1, P01, P10, P11. Now, the reason that this is particularly useful is because the non-signaling conditions, and maybe it helps to just give one example here. So let's say P0000, P0001, P0010, P0011, P0100, 101, P0110, P01. Okay, so the non-signaling conditions, something like what I've written here, amounts to taking these, summing them up. That's summing them up this way. This is when you fix one of Bob's for 0, and then also summing these. And these two numbers in blue should be the same. And in fact, you're going to have, now it's easy to see why there's 8 of them. I have one for when I sum over, give Alice having outcome 0 for this setting. Then I have another one. So basically I have 4 rows altogether that need to have these conditions imposed. And then also 4 columns. So I will also have so then I also have 8, 9, 6, So each of these non-signaling conditions, like normalization, force me to represent some of the probabilities in terms of the others, but they're not independent from normalization. For example, the non-signaling conditions tell me that this plus this equals this plus this, and this plus this equals this plus this. If I add up these two equations together, it's telling me that the sum of all these 4 equals the sum of all these 4, which is already guaranteed by the normalization constraints, because if all of these sum to 1 and all of these sum to 1, then they are equal to each other. So you actually have that there's 8 non-signaling, 4 normalization, but there's actually 8 independent linear equality constraints. So what that implies is that the actual polytope NS is 8-dimensional. I require just 8 coordinates to fully specify a non-signaling distribution. So let's give some convenient representations. So convenient coordinates. One of these I think we've discussed before, which is P of S given X can be written in terms of expectations. So it's 1 plus negative 1 to the S0, A 0, X0. I will define these in a second, plus negative 1 to the S1, A1, X1, plus negative 1, S0 plus S1, E of X0, X1. Where AI xi is equal to the sum over Si P of Si given xi times -1. So this is, we have an outcome which is plus or minus 1, and we're taking its average. So this is an expectation value, and we can define an expectation value for each of the parties and each of their measurements. So there's 4 of these. So this is for I, comma, xi. So there's 4 of these. And then there's these. These are the correlations between them, between the variables. So x0, x1 is defined as sum s0, s1, p of s0, s1, -1 to the s0 plus s1. So these are the correlations. How many of these are there? There's one for each choice of x0 and x1. So this is x0, x1. So there's 4 of these. So we have precisely that I can write down any probability in terms of these expectations. There's 4 local expectations and 4 two-party correlations. So we can write down any probability table like this using these expectations, for example. And so let's just do a quick little example to show how these notations work out. If we look at this, Pescu or PR box. So in terms of the box notation, we have that this box is given by we give 1/2, 1/2, 1/2, 1/2, 1/2, 1/2. We have something precisely like this. So what is this in terms of our expectation coordinates, which maybe I've covered? So what we have is, so these local expectations, what are these? Here we have that the marginal probabilities are 1/2. So if I sum over this and I have probability 1/2 of this being plus, 1/2 of it being minus, the local expectations a, I, xi are equals 0 for every I, xi in 0, 1. Okay, now what about the correlations? Well, the correlations are going to be plus or minus 1 or somewhere in between, depending on this expression here. This expression is going to be plus 1 when they're both the same and minus 1 otherwise. Here we see that the probabilities are always the same, always the same, always the same. So E of 0, 0 equals E of 0, 1 equals E of 1, 0 equals plus 1. This one, the outcomes are 0, 1, and 1, 0. So they're always anti-correlated. So here we have 1, 1 equals minus 1. I'll have you guys point out, maybe this is something worth noting right now, is that if you recall the CHSH inequality, it also had a very similar form. In fact, there's a sort of dual relationship between the PR boxes and the CHSH inequalities. What were the CHSH inequalities? They were something like E00 plus E01 plus E10 minus E11 greater than or equal to 2. It turns out that this PR box is precisely the algebraic maximum. So if I plugged in these actual expectations here, so let's call these the expectations for the PR. Then we see that the actual value of this thing will have a CHSH value of +4 greater than 2. So this box here is non-signaling. And yet it still violates the CHSH inequalities in the maximum way. But this cannot be obtained in quantum theory, it should be noted. Okay, so now what I want to talk about are local or classical models. So what did Fine's theorem tell us? So Fine's theorem tells us that a local ontological model in the CHSH scenario, I'm leaving out some of the additional qualifiers, a local ontological model in the CHSH scenario is equivalent to a joint probability distribution over the outcomes of measurements. So we had something like P of, say, we'll get to this eventually, but I have a set of outcomes, which eventually I will label as 0, 0, A01, A10, A11. So these will be the outcomes of measurements in the CHSH scenario, and that this can always be constructed if you have a local ontological model. D lambda, P of lambda, and I will just write this in short, product P of A, let's see, I product over Ix, Pix given Px, let's see, Pixi perhaps, something like this. The point being that you can always construct this joint probability distribution if you already had a local ontological model to begin with. And if you started with, and you could always construct a sort of canonical local ontological model if you have a joint probability distribution. We talked about this last time. But the key here is to identify that what we've done here is something very non-trivial, is we've defined a tuple of outcomes, and this thing will be called a global outcome assignment. Okay, why is this non-trivial? This is non-trivial because what you're saying is I have all these different measurement settings, and some of them can't be done at the same time. So Alice can't choose her measurement setting 0 and 1 at the same time. And yet we are defining a probability distribution over unobserved outcomes. So there's a very sort of basic, crucial physical assumption that goes into being able to write something like this down. So we're going to formalize that a little bit because essentially what we're going to want to do is we're basically going to restrict our focus to this. Fine's theorem tells us that we can just focus on the joint probability distributions. there's going to be a distinguished set of probability distributions that are called deterministic. And with those, we're going to be able to sort of identify all non-signaling distributions that are classical, that is, they come from a joint probability distribution, in a particular way. So our job, in the next little bit, is going to be to construct what we call the Bell polytope, based off of all of those probability distributions, all those non-signaling distributions that come from a joint probability distribution. Okay, so first, let's talk about global outcome assignments. So this part will be just a little bit formal, but maybe it helps to start with an example. The idea is just that we have a set of 4 different kinds of measurements, and what we want to do is define, I will just define it, a map O for outcome, and it's going to go and take each of my possible measurement settings. So maybe it will be useful to just write it down. My set of measurements are going to be given by precisely which party and which measurement that party is doing. So the set of total measurements are indexed by I, comma x, where I and x are 0 or 1. Party 0 or 1, measurement setting 0 or 1. How many in total? There's 4 of these. Four measurements. Okay, and so when we talk about a global outcome assignment, I'm going to write it down like this, but really it's just a tuple of zeros and ones. So what is this thing? It's a map from M to assigning a value of 0 or 1 to each of these. So what is that going to look like? That's going to look like O is equal to A00. 0. Alice does measurement 0, and it takes value A00 is 0 or 1. A01, A10, A11 in 0, 1 to the 4th. We have 4 possible coin flips, essentially. So what are the total number of possible outcome assignments like this? Well, it's just the number of possible ways that you can do heads or tails on 4 coins, which is, so we call curly O is the set of all such maps. And this is just going to be in bijective correspondence with, so the total number of such maps is just 2 to the 4th equals 16. We have 16 possible global outcome assignments. I should make a comment here that it's slightly confusing, but just a coincidence of the CHSH setting that the total number, and so I'll call this K, that K happens to be equal to the total number of empirical probabilities, which is also 16 in this case. But it will be important to give it a different sort of letter to prepare ourselves for other scenarios where these numbers don't work out exactly the same. So with a global outcome assignment, you can define something called a deterministic distribution. So what I want to do is say I have some distribution P tilde going from O to the non-negatives such that the sum. So this is just, I'm calling this a probability distribution. We have some p tilde, it's a probability distribution. I'm gonna play a little trick here. I have p tilde of O prime. So me evaluating it for some tuple, like one of these over here, I can do this very trivial thing. I'm summing over all O's. I introduce a delta function. So I will do this over O. Delta function O prime, where delta function O tilde of O prime is equal to 1 if O equals O prime and 0 otherwise. So this is precisely a delta function, but you can also interpret this as a distribution. I can think of this probability distribution as being given by a sum over these delta tildes. I mean, so putting it somewhat more formally, you can sort of think of these as being basis functions. So I have functions going from O to R, say, and I can write any function I want actually as being the sum over O f of O delta tilde O prime. This is just a basis for the set of functions O to R. Now this is just when I restrict my coefficients to be convex. So I can sort of think of this geometrically as well. I can maybe abuse a little bit of the notation and think of these abstractly in some vector space, the vector space of functions going from O to R. And then I can think of the convex hull of those. So this is sort of like the simplex picture. In fact, it's geometrically just precisely the same, but I've decided to rewrite it in just a little bit of a different way. The benefit of this is that what can we say about this distribution right here? In fact, it's a product of distributions, because what does it mean for this to be the case? Delta of O prime is precisely saying that I have to have, using this tuple notation, I will denote O primes with A primes. Basically, I'm just saying that I have a product. Maybe it will be easier to write it like this. Product AX in 0, 1 of delta AIX prime. So I have a product of delta functions, and that's what defines this delta distribution right here. And this is a basis for the set of functions. Okay, which is a long-winded way of saying that actually it's a good idea to restrict my attention for the time being on these basis functions, because everything else can be obtained as a convex mixture of these. So this is a very important point. I can just restrict my attention, and then everything else is just a convex or probabilistic mixture thereof. So here we have these very special delta functions. Well, maybe that's a little misleading. So basis / extreme So if I start with, so because I can sort of restrict my attention to these delta functions, I want to see that these are actually going to give me some of the properties that I want. Like, are these non-signaling? Clearly they're normalized, because if I sum over all these elements, I'll definitely get 1. But it helps to just sort of see how non-signaling shows up as well. So let's define the corresponding non-signaling distributions. So if I start from a joint probability distribution and then I restrict my attention to these deterministic joint probability distributions, these are the ones that assign a particular value of outcomes. Then how do I get an empirical distribution? Well, I get the empirical distribution by marginalizing over certain outcomes. So I will call the empirical probability that I get for a particular, so let me fix some measurement settings, some context x, and I'm going to call this thing d0 of s0, s1, x0, x1. Let's specify further. Now, this is a joint probability distribution. So if I just want to get certain outcomes, I will marginalize over the others. So I'm going to introduce a funky little notation, but hopefully you'll see how this works. I want to sum O prime in, what did I call this? X of S delta 0 O prime. And I claim that this thing will be equal to delta S0 comma A0 X1 delta S1 A1 A0 X0 A1 X1. Okay, so I will get a product of Dirac deltas. What am I doing here? Say I pick some context and there's some outcomes S0 and S1 that I get as outcomes during this measurement procedure. Then, in order to actually get the empirical probability starting from here, I should sum over some outcomes. Which outcomes precisely? I want to sum over all the outcome assignments that agree with S0 and S1 when X0 and X1 are being measured. So this set here, and I will do an example to sort of say what I mean more explicitly. These are the outcomes such that A0 X0 equals S0 and A1 X1 equals S1. So what does that look like? Say I choose X equals X0, X1, then, and say that's 0, 1, and then also let's pick some outcomes S equals to, S0, S1 equals 1, 0. Then how do I pick these? Well, what I need to do is pick all the outcome assignments, all the tuples, such that A0, 0 equals 1. So when Alice picks 0, the outcome should be S0, which is 1, equals S0 equals 1. And A11, Bob, party 1, chooses measurement 1 and gets outcome 0. So, which are the possible O's that I have there? Well, O of X of S is going to be precisely all those tuples, which are 1, A prime. So maybe I write these out completely explicitly. A01, A10, 0, where A01, A10 are 0, 1. There's 4 possible choices here. 1, 0, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1, 0. So 0, 1, 1, 0, 0, 0, 1, 0, 1, 1, sorry, 0, 1, 1, 0, 0, 1, 1, 1, 0. So what we're doing over here is we are just summing over these 4 elements to give us precisely, and because we're summing over these deltas, I get precisely a product of the remaining deltas, because I'm summing over 2 variables gets rid of 2 of the delta functions. I'm left with a delta function over 2 pieces. And clearly this is also non-signaling, because now if I sum over S0 or S1, it just gets rid of the other delta function, which does not depend on the other outcomes. So if I do sum S1 of D0 of S0, S1, X0, X1, this is sum over S1 of delta S0, S0, A0, X0, delta S1, A1, X1. So this is just going to sum over this, give me precisely kill this sum so that I just get this. Which is precisely non-signaling. So in general, we can actually, continuing from over here, the deterministic non-signaling distributions can be written as D0 of S given X, S, comma X. So these are just going to be products of delta functions. So what's that going to look like in the box notation? So say, for example, I pick the 0 such that equals all zeros. Then I have that for this one, I'm going to have Alice choosing measurement setting 0, Bob choosing measurement setting 0. They're both going to get 0 with probability 1 and zeros everywhere else. Similarly, 1, 0, 0, 0, 0, 0, 0, 1. And similarly, we can also think of these as vectors in some Rn in the same way. So in general, what's going to happen here, what do we mean by a classical non-signaling distribution? Well, for any p tilde of O prime, we had that it is a sum O over O, p tilde O, delta O, O prime. So this is a convex mixture over these deterministic tables. So we have that the corresponding non-signaling distribution is going to be a sum O in O weighted by these tildes, p tilde of O, and the corresponding boxes, which are all going to be the corresponding delta functions like this. It looks like maybe I was a little bit fast here, so let's see how that happens in a little bit more detail. But it's maybe not so hard to believe that what's happening here is you have some element in R16, and then I'm mapping it into a product of distributions here, and this thing will hopefully be linear, which I'm going to show right now. So suppose that we had some empirical distribution coming from a joint probability distribution. So it looks like S0, S1, X0, X1. And the way that we obtained it was precisely by summing over O prime in O of X of S. That's that set that we designed before. So we're just summing over all of the outcome assignments that agree with S0 and S1 when these are performed, just as we did before. We're going to play our trick where we rewrite this joint distribution. So we have the sum O prime over O of X, sum O of P tilde of O, and now the distribution O of O prime. I'm going to switch the order of these sums, O in O, sum O prime of delta O, O prime. Now this is precisely the empirical probability that we computed before. This is nothing but a product of delta functions. So, and we will just call this, so this is sum O in O of P tilde of O times D0 of S of X is equal to P of S of X. So what is this showing? That for any choice of X and outcomes, if I started from a joint probability distribution, I can think of these, the empirical probabilities obtained in this way as being the deterministic empirical probabilities. That is, you have a delta in each of these boxes, weighted precisely by the p tildes that are coming from the joint distribution. So we say that a non-signaling distribution is classical. Is classical if it comes from some joint probability distribution. In other words, the corresponding non-signaling distribution is going to be sum O over O P tilde of O D0. And D0 is precisely what I mean by a box of this form, something like this. So this is what we mean by classical. By Fine's theorem, this is also what we mean by local in this case. So we can be a little bit more formal than this, but it helps to do an example. So maybe I will go right here. The example is as follows. Let's assume that I have two outcome assignments. Let's say, what do we call them? 0, 0, 0, 0, and O prime equals 1, 1, 1, 1. And we have a joint probability distribution that gives P of O equals P of O prime equals to 1/2. What is the corresponding non-signaling distribution going to look like? Well, it will look like 1/2. This one is the one that I just erased. It gives a 1 in the upper left corner and 0 everywhere else, weighted by probability 1/2, plus 1/2 times the corresponding distribution here. What does this look like? When Alice chooses measurement setting x0 and Bob chooses x0, the outcome is 1, 1. So that's the bottom right corner. And it's the same for all of these. And 0 everywhere else. So that the non-signaling distribution is precisely of this form. One-halves on all the diagonals and 0 otherwise. So a little bit more formally, we can define what's called the Bell polytope. And what is this thing? This is defined as the convex hull over all outcome assignments and the corresponding non-signaling distributions. So this is precisely all non-signaling distributions that can be written as I've written them up here. That's equal to all P such that next time, we're going to talk about exactly how one can witness a separation from this polytope. So we can think intuitively of the Bell polytope as something like this. And then maybe the non-signaling polytope, well, it's a subset of that. So we have something like this. This is NS. This is L. How can we witness whether a non-signaling distribution P is inside of here or not? So those are going to be called Bell inequalities. And next time we discuss Bell inequalities of various kinds, ones that are trivial, ones that are tight, the facets of this polytope which distinguish every P. Okay.